Okay, everyone. Just to have your attention, welcome to the new semester. It's a pleasure to have today one of our own, Pete, from the Department of Electrical and Computer Engineering. So I don't need to say many things, just, I want to express my personal, point of view that, Pete, for me, is an example of how you can marry practice and theory. So it is not like, a surprise that he has like best paper awards in ACC, for example, NSF careers, and he has done also like much collaborations with industry, like MathWorks, Boeing, and NASA, if you could call NASA industry anyway, but you get like Boeing. So yeah, today he's talking about the topic that is a lot of interest of me and especially some of my students, robust online convex optimization for control applications, in particularly disturbance rejection. So yeah, with much pleasure, I look forward to the talk.
All right, thanks for the introduction. So then, since this is the first seminar of the semester, I should also say in Professor Frudenberg's absence, we should thank our sponsors, which are Seagate and Toyota. So if you want coffee and cookies, you can thank them. So I'll thank them for everybody. Okay, so I came in January 2020, excited to be here. I think I gave one of the first seminars that semester, which was winter, I guess, 2020. And then of course, COVID hit just like a couple months later. And this is the next time that I'm going to talk. So I'm excited to do it again. So what does this talk about? I'm going to talk about online optimization. I'll clarify this as we go along. And it's for applications where there's high precision. I'm going to talk at length about one of them that really motivated why I'm going to work on this. And often in industry, you may do classical control, and I'll talk about why that's maybe insufficient in these applications. And if you do online optimization, then it can turn out that there's a model that's going to be embedded in what I'm going to talk about, that can lead to instability. And so what I'm going to describe is how can we kind of marry these ideas. I want to do online optimization, but I also want to be robust to these type of model errors. And so these kind of key contributions I'll come back to at the end. This is really a paper that was worked out. I should have mentioned this on the first slide by my student Joyce Lai, who's here, I guess, sitting in the back somewhere. So she'll be presenting this at the 24 CDC, and there's also an archive version. I also want to acknowledge sort of the NSF grant that's supporting this work. Okay, so I'm going to talk through why we're doing this in an application having to do with satellites. I'll talk about what's the fundamental limit of performance if you only do LTI control, linear time invariant control. That's going to motivate why you might want to do online optimization, which will give you a class of nonlinear and or time varying controllers. There'll be some stability issues here, so then we'll come down to like what's our key result to kind of prevent that from happening, and then I'll wrap up. Okay, so let's jump into the first part. What's the motivation here? In the past few years, I've gotten involved in a lot of satellite pointing problems. Those satellite pointing problems could be imaging. I'm going to image something on the Earth, or maybe I'm going to image some star far away. Another application is two satellites communicating to each other. So here's two companies that are trying to do this, Starlink, Amazon, they have their Kuiper program. They both have the same idea, and there's others as well, which is have this constellation of thousands of satellites in low Earth orbit, 500 to 600 kilometers up, and then beam internet anywhere in the world. That's the concept. Now, what's the basic operation? So you can find all these documents. The FCC is the commission in the US that handles or regulates communications on the Earth, terrestrial communications, which also includes communications from the ground up to satellites. So Starlink has a whole bunch of these, FCC filings of what they want to do. So back in 2020, they filed one that said, we're approved for 7,500 satellites. We would like to hop data in one of two methods. Originally, the way they were doing it is start from here, and I want to communicate to somewhere else. And I'm going to do this bent pipe connectivity. I'm going to communicate up to a satellite, come back down, and kind of hop this way. Okay. So I'm not doing satellite to satellite communication. I'm going from ground to satellite back down again and just keep doing that. That requires you to have lots of Earth stations in order to do this. Originally, they were in this kind of 10 to 30 gigahertz band. Now, very recently, this was just in the spring. Now, maybe they've changed the frequency. Now they're up around 70 to 80 gigahertz. And there's another 22,000 satellites pending approval. So you can see this, we're talking about 30,000 satellites potentially just for their kind of mesh network in the sky. They've also been approved, or what they're going to attempt to do, which I'll talk on the next slide, is maybe do satellite to satellite communication. Now, why would you want to do that? That's this optical inter-satellite links. If you're communicating data along the ground, you're using, terrestrial fiber optic cables. That has a certain latency. If you're doing it in space, you're basically sending light through a vacuum, so it's faster. Now, why is that important? Well, if this is London and this is New York, then being able to transmit data from New York to London 5 milliseconds faster means you can do high-speed trading and you can make millions of dollars. This is one of their case studies. Like, those are the people that are paying money for all this, I guess. So, okay, so that's one reason to do this. So they launched some satellites in 2021. There's some links, kind of popular press links. So they had some prototype satellites. There's really not a lot that's written about what exactly they're doing in the space. As far as I can tell, because the FCC governs these links, there's all sorts of government filings that say kind of everything they're doing. There's like some guy in the Air Force, his name and email. If they're going to have a satellite go over some part of the Air Force, they got to email this guy. That's in the document. There's all sorts of information. These links, though, I could find very little. Okay, so that's kind of interesting. Amazon also did a similar prototype test in late last year, December 2023, where they did communications between two satellites. The frequency here is unclear. The previous slide, the frequencies were about 80 gigahertz. This, most people think it's in the terahertz range, hundreds of terahertz. So it's about 1,000 times faster in frequency. That's going to be important in a moment. Okay, so along the ground, the frequencies are 1,000 times lower than in space. And I'll explain why that is in a moment. And that'll impact the control design. Why optical links? Like, why work in this terahertz range? So imagine I have a laser on one satellite. I'm going to communicate to another. The laser basically has a certain aperture, a certain width that I'm shooting the laser out. And then the beam is going to diverge. The relationship between this divergence angle and then the width of the radius on the laser is kind of given at the top. So it's related to the wavelength divided by the width. Okay, and there's a factor of pi in there. Now, the wavelength and the frequency are related by the speed of sound. So if you go to higher frequencies, you get smaller wavelengths. Okay, that's the basic trade-off. So if you go to a frequency that's 1,000 times higher, you get wavelengths that are 1,000 times smaller. Now, there's a bunch of consequences to this. Because the beam is not diverging as much if you're at a much higher frequency, you need lower transmit power. You're able to direct the beam more precisely to what you're kind of aiming at. That also means you get higher signal-to-noise ratios and you get higher data rates. It also means you can make the receiver transmitter part of the laser can be much smaller. You can choose smaller widths. And then there's a security aspect as well. If you can make a narrower beam, it's less likely that somebody could try to intercept the data that you're sending. Okay, so there's lots of reasons to be doing this at a very high frequency. Now, what are the challenges? This is coming from one of the Amazon press releases. To maintain these laser links, you need to basically point very accurately, because if the beams are going to be very narrow. If you're off by a little bit, you're not going to receive the data on the other end. The distances between the satellites they've given there, maybe let's say 2,600 kilometers, and the satellites are moving at speeds of about 15,000 miles per hour or 25,000 kilometers per hour. And so you basically need to have these satellites that are moving relative to each other point very accurately at each other. Okay, that's different than maybe a space science mission where you have one satellite and you're pointing at a star way out in space, or maybe you're just pointing at some fixed point on the ground. These two satellites need to maintain connection and be constantly pointing at each other. Okay, so it's a very challenging problem. And so just to give this some context, let's say the receiver on the satellite is a half a meter. That's about the size of a basketball. And you're going to transmit 26,000 kilometers or 2,600 kilometers away. So I've given the angle there. It's a 0.01 arc seconds. So there's a NASA report that says problems in this range are very difficult, and they may require you to cherry pick components, meaning if you put a reaction wheel on a satellite, which is something that spins to help point the satellite, you may buy 100 of them and only pick the best two. Okay, that's fine if you're doing one space satellite mission, like NASA usually builds one or two, they launch them and that's it. You can cherry pick stuff, that's fine. If you're gonna build 25,000 of these or 30,000 of these, you can't resort to cherry picking. Like, you got to buy a bunch of reaction wheels, you just got to use them all. You got to buy a bunch of sensors, you got to use them all. Otherwise, it's not going to be financially feasible. Now, just to give you I did this yesterday. What does it mean to hit something of a radius of a 1/4 meter at a distance of 2,600 kilometers? Okay, so there's Ann Arbor. The Earth is a sphere, so it's flattened out. So the sphere this doesn't quite look like a circle, even though these are all the things on the Earth that are 2,600 kilometers away. Boise is about here. So you're going to hit a basketball by aiming a laser from Ann Arbor to Boise, and you're going to hit a basketball. Okay. Phoenix is down here. The farthest point on North America east is over here. Okay, that's Cape Spear. There's some points in Mexico. I forget what cities are down there, but Okay, so that gives you some, like, these are very precise pointing requirements. Layered on top of all of that is, we're not just building one. We're going to try to build 30,000 of these things that all work well, all can communicate with each other. Okay, so now let's get to what's the control problem. That's kind of the setup. There's a lot of feedback loops here. There's feedback loops on the satellite itself. If you're in the aero department, you probably maybe take a course. I don't know if this is covered in your course. You talk about how you point the satellite itself. On the satellite, you may have the transmitter and receiver, which is up here. That's sitting on some gimbals. So you can kind of roughly move that thing around. So the beams are coming in and out of there. Inside that little transmitter receiver box then, cartoonishly, it might look something like this. Beams are coming in, they're bouncing off certain mirrors. There's a what we call a fine steering or fast steering mirror that then points things to the receiver or also points things kind of going out. There's multiple loops here. I'm going to talk literally about the very fastest loop, which are these fine steering or fast steering mirrors. So if I say FISM, I either mean fast or fine, I mean kind of the same thing. That these mirrors are basically, once you've done all the coarse pointing, they're doing the final like focusing in, and so you get the highest data rates. And so that's where I'm going to talk about kind of the basic control problem here. Okay, so now I'm going to abstract this away and just think about, well, what's kind of happening as the way we might teach it at an undergraduate level. So this fine pointing or this fast steering mirror control looks like the following. There's some plant dynamics, which are really these mirrors. They have flexibility to them. Okay, so they're somehow a little bit flexible at very high frequencies. And there's these disturbances coming in. Why are there disturbances? Because all this is sitting on a satellite. The satellite has reaction wheels, which are kind of causing it to turn, but then those are creating vibrations. Those vibrations then transmit themselves all the way up to this mirror. So there's a bunch of disturbances that are coming in. These disturbances are changing in time. Okay, there could be one reaction wheel is spinning and it's changing its frequency, causing the disturbances to act at some frequency. Then it's acting at another frequency. So we don't know it ahead of time, but there are features that are learnable. It's not like when we take, our state space control class, we might talk about white noise. A white noise disturbance is kind of, there's nothing to learn. It's purely random. Here, there's something to learn. I just don't know what it is ahead of time. Very stringent performance requirements. That's kind of what I was starting from, is just to motivate that you really need this signal to be, not varying very much at all. The models are going to be imperfect. We can measure them on the ground, but you're going to launch this thing into space. The environmental conditions are changing. There's part-to-part variations if you're going to launch 30,000 of these. So we don't have perfect models here. And then similar problems arise in other applications where there's kind of high precision problems. Hard disk drives for cloud storage, photolithography, and so on. Okay. So this is the abstraction that I'll work from. Now, the first question is, well, why not just do things the way we've always done them, which is like we teach undergraduate classical controls. We do basic PID design or loop shaping or some other method. Why is that potentially going to fail? Well, let's think about what are the fundamental limits of what I could possibly do if I even know kind of the disturbance properties. Let's not even worry about the fact that the disturbance is changing in time. So if you close the loop here, if the plant's linear time invariant and your controller is just a linear time invariant controller, the transfer function from disturbance to output is the sensitivity. Okay, that's given up there. And let's assume that the disturbance is stationary. And let's assume it's zero mean. I can even tell you what the power spectral density is. So I tell you, like, if I plot the energy, or the power, I should say, of the disturbance as a function of frequency, this is its, that's what it is there. Okay. Now, what's the minimum variance output I can possibly get by designing a controller? That turns out to be a very special optimal control problem. LQG or H2 would be the type of problem. And so you could find the optimal controller if I tell you what the power spectrum is. I'm not gonna go through that because that would just give you the controller. I want to go down a different path. And the path that I'm going to tell you is going to give you an analytic expression for how good can this possibly be if I tell you what that disturbance spectrum is. So here's how we'll go about this. I'm going to assume, again, that the power spectral, that the output is also, or the disturbance is zero mean. I've given you its power spectrum. I've told you the transfer function from disturbance to output is the sensitivity. So this is the relation that governs the power spectrum from the disturbance and how it's transmitted to the output. It's governed by the sensitivity magnitude squared. What's the variance of the output? It turns out the variance of the output is this factor here. Take the power spectrum of the output and then integrate. And because I'm only integrating over half the frequency, the rate scaling factor is 1 over pi. So take this expression and kind of put it in here. Now, the disturbance then is going to be attenuated at frequencies where you've made the sensitivity small. Okay, so if this is less than 1, you've attenuated where the disturbance is. And if this is bigger than 1, you've actually amplified the disturbance. Okay, so our goal is to try to make the sensitivity less than 1 basically everywhere that we can. That's what we would like to do. And then we'd be attenuating the disturbance. Now, it turns out that you can't do that. There are constraints on you can't make the sensitivity less than 1 everywhere. And so let me just talk about that before we come back to what the basic result is. If the plant is stable, and I didn't do any control at all, so just set 0 for the controller, then the sensitivity is just equal to 1. So if I plot sort of a Bode plot of the sensitivity versus frequency, 0 dB means the sensitivity has a gain of 1. And so in that case, if you were to integrate the log of the sensitivity, it's just equal to 0. Okay. So if you don't do any control at all, the sensitivity is equal to 1 at all frequencies. The variance of the output is exactly equal to the variance of the disturbance. We haven't done anything yet. We'd now like to see, well, what's the impact of doing control? Well, ideally, the control will reduce the variance in the output. And so now we get to kind of this fundamental constraint, which is if I get a sensitivity, often it'll look something like this. The sensitivity will be small at low frequencies, close to 1 at high frequencies, because usually at high frequencies, this quantity is going to 0. And then in some mid-frequency range, it'll actually be bigger than 1. Okay, so bigger than 0 on this log scale means the gain is bigger than 1. Okay? So the controller is making things better down here. It's making things worse down here. If it happens that your disturbance has a lot of energy here, you can actually make things worse by doing controls. Okay? And that peak is basically a basic consequence of doing control. And so it's a consequence of the Bode integral theorem, which is if the loop, which is the product of G and K, has a relative degree of 2, and I tell you that the loop itself, G and K are stable, and the closed loop is stable, then it turns out that this integral here is exactly equal to 0. And if you want to do this in units of dB, the same thing holds. The constant of dB just changes the scaling constant in front. You still get a 0, okay? There's a result due to Bode, and actually Professor Freudenberg did a bunch of seminal work on this in the late 80s, just to kind of like flesh out all the things that are kind of happening in this type of fundamental constraint. So this is, I would say, the key conserved quantity in feedback design. If you try to make things better, at least with linear time invariant controllers, if you try to make things better in some frequencies, you're making things worse in other frequencies. Okay, now I'm gonna skip maybe this slide just in the interest of time. Now I'm going to go to like, what does this tell us about how good we can do things in terms of disturbance rejection? So now let's come back to our disturbance rejection problem. I've got a disturbance coming in. It's going to cause the output to bounce around a little bit. And we said the sensitivity is what's connecting those two. And I would like to know how small I can make this variance. Okay? So I'm going to try to solve a problem where I'm not going to worry about actually solving the controller. I'm just going to ask, what does the sensitivity have to look like to get me the best possible disturbance rejection performance? So that type of problem is going to look like the following. This quantity here is actually the variance in the output. Okay, this is the power spectrum of the output, just I've plugged in for how it's related to the disturbance. So I want to minimize the variance of the output. What's the constraint? The constraint is the sensitivity function when I integrate it over frequencies has to be equal to 0. And it turns out for various practical reasons, the upper limit here isn't infinity. You have things like Nyquist sampling theorem and all sorts of other things that there's some upper limit where this integral actually has to equal 0. Okay, so that Bode sensitivity integral here, that's the constraint here. I can't pick any sensitivity I want. It's got to satisfy this basic fundamental constraint. So now I'm going to solve this problem, and the solution ends up looking like the following. So it's lots of things on the slide here, but the optimal variance, the minimal variance that you can possibly have, breaks out into 2 possible terms. The first term is integrating from this kind of fundamental or this basic, upper bound on due to like the practical reasons, this omega A out to infinity. That term basically says I can't reduce the disturbance at all at high frequencies because I've got all these other practical effects, Nyquist sampling theorems and so on. So there's a part of this that I just, no matter how I design the controller, I'm not going to affect the disturbance at high frequencies. It's really the first term where you can actually improve things through control. Okay, the constant is written up there. The first term through Jensen's inequality, it's whatever that is. It turns out it's less or equal to what you would have had in open loop. Okay, that means This is the part where you're actually making things better through control. And how much you're making things better depends on what the disturbance spectrum properties is. You can also back out what does the sensitivity have to look like. Wherever the disturbance is large, you could imagine the sensitivity has to be small. I have to do a lot of control action there. Okay. If the disturbance is white noise, then it turns out that this power spectrum is constant at all frequencies. And then if you just plug everything in there, it turns out that the optimal variance in the output is the variance of the disturbance. So this consequence tells us, like, if you just have white noise disturbance, no point in doing control. You're stuck with what you have. There has to be something learnable in the disturbance. Okay. So this is all to tell you, like, or maybe to motivate, like, why might you want to think about like non-linear time invariant control? If I have a case like I've tried to motivate with these satellite pointing problems where there are disturbances, they're not just pure white noise, but they're changing in time, it's possible then maybe I can do online optimization. I could try to learn the disturbance online. I could try to counteract them. I could try to get below this limit that I could possibly get just using linear time invariant control. That's the basic idea. Okay. So now we're gonna, let me see, what else did I want to say here? Okay, I've given the optimal sensitivity gain. This just says what I said before. Wherever the disturbance is large, the sensitivity has to be small and vice versa. And whatever the optimal sensitivity shape is, this is kind of some mathematical structure. You may not actually be able to implement this. Okay, so now let's go to, now that I've hopefully tried to convince you that there may be some utility for online convex optimization in this application, let me try to describe some ways that you might go about doing this. Now, disturbance rejection doing online optimization actually has a long history. If you have noise canceling headphones, you have some form of like, hey, I'm measuring what the noise is, I'm gonna try to counteract it. So you might say, well, this has already been done. You know, recursive least squares and least mean squares, these are algorithms that have been around for a long time that I'll talk about. What's new here? Well, noise canceling headphones are a little bit different than this problem. Why? In a noise canceling headphone, they have a little microphone. They measure what the disturbance is. Once they measure what the disturbance is, then they can try to figure out, well, what do I need to put in as a speaker to kind of offset that and cancel it out? In our problem, we don't get to measure the disturbance. Okay, so there's something fundamentally different. It's not like we have a microphone here that can measure the disturbance on the satellite or some other sensor that can measure the disturbance. Okay, so it's gonna be something slightly different than those type of applications. But just to tell you, like, there's lots of kind of classical online optimizations that people run. I guess model predictive control would be another one, but I think for disturbance rejection, maybe this is a slightly different formulation. Professor Bernstein's done a lot of work on what he'd called retrospective cost adaptive control. I guess maybe you've also done some work on this. I don't know. So some of these things I don't know necessarily all, I don't know all the connection, but there's lots of kind of work. But then more recently, there's a surge of work, I would say, by people maybe who are more machine learning kind of in their background. And they use what are called regret-based formulations. So just briefly to talk about this isn't really the crux of this talk, but what's the context of these regret-based formulations? Often on the control side, when we formulate optimal control problems, we say, how I formulate it, let's try to minimize the variance. Okay, that's a reasonable thing to optimize. That leads to things like linear quadratic regulator, linear quadratic Gaussian, H2 optimal control. These would be kind of standard optimal control problems in the control formulation. These regret-based formulations would say, well, it would be better if I try to optimize relative to some baseline. What baseline? Well, suppose I knew the entire disturbance ahead of time and I designed the controller with perfect knowledge of the disturbance. That's like a non-causal controller because I tell you the entire disturbance ahead of time. And then I'll try to optimize my controller. My controller won't know the disturbance ahead of time, but I'll try to optimize my controller to be as close to that as possible. That would, I'd say, is roughly what people are trying to do with these regret-based formulations. And that's born from, like, I think the way people in machine learning solve certain online optimization problems. So there's a whole literature here, which I'm not going to go into, but I'll just, as an aside, say there's another paper by one of my students that kind of deals with that regret-based formulation that, if people have questions, I can talk to. Okay, so there's a big literature here. I'm going to talk just about the most basic version, which is recursive least squares. So here's what it's going to look like. I've got the same setup before. Now I've added one more loop here. So what's going to happen here? Imagine I've got a baseline controller. I've just designed some classical controller to partially cancel this disturbance. And this is bouncing around too much. So on these satellite problems, the variance here is too big. I can't maintain the right communication link. So now I'm going to try to add this additional loop, this optimization loop outside. And it'll use recursive least squares and hopefully improve the disturbance rejection performance. So here's what it's going to look like. Ignore the recursive least squares for a moment. So I've said I'm going to switch to discrete time now because it'll be easier to describe what I'm doing. So you're going to see Z transforms now. I'll switch to discrete time. So from D to Y, I said that the transfer function was the sensitivity. Okay. So if I have the baseline controller and there's some disturbance coming in, hopefully the output is bouncing around less than the disturbance. So I'll call that kind of effective disturbance. I'll just call that W. Okay, so that's how much disturbance is left over after this baseline sort of design. I also want to know what's the transfer function from this point, which is usually where a reference comes in to the output. That's denoted as T. That's the complementary sensitivity function. I want to know that because that's where I'm going to inject this additional like recursive least squares input later. Okay. So without thinking too much about it, what might you want to do? Well, if I knew what W was, like if I could measure that in real time, what I would try to do in V is I would invert T and subtract off W, right? So just put in here, if I could do it, I would put in -1 over T times W, and these would cancel out and Y would be 0. Okay. Now, that's not really something you can implement in the sense of we can't directly measure W. That's what I tried to convey before. I can't directly measure D in these sorts of applications. I also don't have a perfect knowledge of what T is. I maybe know exactly what I've implemented with my baseline controller, but maybe I don't know exactly what the plant dynamics are. Okay. So instead, what we're going to do is we're going to try to estimate what we think is the effect of the disturbance. We're going to estimate W. Once we have W, then we're going to inject another signal here. And our signal will this looks like a time varying FIR filter. Okay. And our estimate for W is just take whatever we've ultimately injected here, figure out what this signal is based on, I guess, what this signal is, from V to Y, just using our model. That's this piece. Y minus that, whatever's left over must have been the effect of the disturbance. That part's not super important other than just to say there's a simple estimator built into this. And this is kind of what distinguishes this type of application from things like noise canceling headphones. We need to first estimate what we think the disturbance is. We don't get to directly measure that. That may seem like a minor point, but it's not, because what's ending up happening is there's like embedded in here, this feedback is inside of here, we take Y, we estimate W, then there's going to be some FIR filter. There's like this extra feedback loop. And by adding that extra feedback loop can actually cause things to go unstable. That doesn't typically happen in noise canceling headphones. You're measuring the disturbance, and it's more like you're measuring the disturbance and you're just directly feeding in here. There's like an open loop path. Okay, so we're going to estimate the disturbance. We're going to run it through an FIR filter. We're going to try to figure out what these coefficients, these FIKs should be, and then we're going to inject that signal back in. So people might call this a disturbance action filter, at least in this kind of recent work on online convex optimization. And now, this is maybe poor notation, but part of the dynamics are linear time invariant. This part is linear time varying. So now I'm mixing up notation. I guess I should write that in a time domain. You can then plug V in here and you can write this all out as like as a least squares problem. At time n, let's suppose I've run the algorithm for n steps, and I want to figure out, or I run the algorithm for a certain, let's say k steps. I want to figure out what these coefficients are, f0, f1, fn. It turns out I want to minimize y, so that's what I'm going to try to minimize. I can formulate that as a least squares problem at each time step, okay? So the A and B depend in a complicated way on the model T, depend on a complicated way on the W hat, and so on. But you can write it out in these coefficients I'm trying to solve for, they enter linearly. Okay. Now, one thing that's happening is the number of columns of A is the number of coefficients in my FIR filter, but the number of rows depends on the time step. So at time K, I have K rows, and I have K entries of B. And so as time is going on, these are getting longer and longer. I'm getting a bigger and bigger least squares problem, but that's okay. The global solution can be computed by sort of an iterative update at each time. That's the recursive least squares. Every time I get a new sensor measurement, conceptually, I'm adding one more row to A, one more entry to B, but I can take the previous optimal solution for all these coefficients, and I can do sort of an update that involves the previous solution plus this new sample time, and I get a new globally optimal solution. So that's the thing that we're going to look at just for a moment for our algorithm. So I'm going to give you a simple example to show how this plays out. So I've got a plant. We'll assume the plant is in continuous time. I've given you the controller. It's a simple PID controller. The loop bandwidth is about 12.5 radians per second. And then we discretize things. So we'll run everything in discrete time so it's consistent with what I had before. Here's the disturbance. The disturbance has one kind of low frequency harmonic, another piece at a slightly higher frequency, and then it has white noise. Okay. Now the numbers that are relevant here, the white noise part, here's the standard deviation, 0.05. The variance, or I should say the standard deviation of the whole disturbance is 1.18. So we're gonna think of if I did no control at all, that disturbance is going to the output. So I'd expect the output to bounce around with this as the standard deviation before I do any control. So that's kind of the baseline for performance, so to speak. Then for the recursive least squares, I'm going to use this FIR filter, and I'm going to have 10 coefficients. So F0 through F9. And then I'm going to use recursive least squares to solve them. So here's what it looks like. I'm first going to simulate this where I have an exact model of the plant. So for the first 10 seconds, the recursive least squares is off. The output is bouncing around because that's basically just what the disturbance looks like. You can tell there's a little bit of noise, and then you've got the two harmonics that are superimposed. Okay, so the output variance is 0.27. It should be a little more specific. The baseline controller is on here, but not the recursive least squares for the first 10 seconds. Okay, so if I was purely open loop, here's the variance or the standard deviation of the disturbance. Now with my baseline controller, it's been reduced. So the baseline controller is reducing the disturbance somewhat. Now at time 10, I turn the recursive least squares on. Okay, and boom, it cancels almost everything out. Everything that's left over is basically just the noise. And now the standard deviation is 0.06. So that's basically just the noise that's left over in the disturbance. Okay. So if I know the model very well, which in this case I have a perfect model, the baseline controller does a reasonable job, and then recursive least squares kills out everything that's learnable. The white noise stuff, there's kind of nothing to learn. You have a question? Yeah, go ahead.
So the recursive least squares is essentially learning the sign terms that you had in front of the NK, is it?
It's not, okay, that's a good question. It's not learning these. I would say more specifically, if we back up, if this was a time invariant FIR filter, if it converged in steady state, it converges to -1/t multiplied by whatever W is. So it's kind of learning the disturbance, but it's also inverting out whatever dynamics are in the path from V to W. So a little bit of both. Yeah, good question. Yeah.
For the application, don't you need to measure Y at the receiver, or can you actually measure it in the transmitter?
You do get to measure it at both the receiver and the transmitter. Both ends are measuring. On the receiver side, there's a laser that's coming in. Let me back up a little bit. Let's think about on the receiver side. There's a beam that's coming in. Some of these are fixed mirrors. This one can move. It's actually two axes, but let's just focus on one axis. These mirrors are kind of partially glazed. So some of the beam comes down here and some comes into the receiver. There's a sensor here. So you're trying to keep basically a laser on the dot in the center of the dot. So I can measure exactly where the laser beam is. And so I basically can measure Y almost perfectly. That part isn't really the issue. And if this laser beam is not perfectly on the dot, I'm not getting all the energy going into the receiver.
Yeah, I think my issue was if you are measuring Y at the receiver, so you will need to send back that information transmitter for the feedback. Isn't that complicating the issue?
I don't think that they do it that way. That's not my understanding. There's a link. I should be a little more precise. There's a period where they're linking up. Once they're linked, now these fine precision, like the final, like the beam, you can almost think of as got like a bell-shaped curve. So if you're off by a little bit, you're kind of linked, but your data rate's going down. That part, they're not communicating back and forth to each other. They're communicating back and forth to each other just to even get within the range where they're pointing close enough that this fine precision stuff will work. So there is some talking back and forth, but not at this level of the control problem. Yeah. Yeah, go ahead.
Will the mechanical system like indicate some knowledge for the noise?
Will the mechanical system cause some noise?
No, kind of like, can we learn something from the mechanical system instead of directly from the noise?
Depends on what you mean. There's lots of the mirrors themselves, I'll show you some like what a representative Bodhi plot will look like. So you may mean, can I learn that? Or-
This kind of mirrors, they may have a certain kinds of preference in the noise.
Depends on what you mean by a certain kind of preference in the noise, like,
Some specific mechanical system, they will provide noise in a certain kind of form.
I would, roughly speaking, I would think of these as like lightly damped second order systems. And then you're gonna see there's like lots of like high frequency, like flexible structural mode type stuff. So to some degree, they can cancel all the noise up to a certain bandwidth, and then beyond that, it's just outside the bandwidth. I don't think there's a preference in the low frequency range for the noise properties. Yeah, go ahead.
Do the disturbance properties change? Like,
They do.
so if they're changing, how quickly can the filter update based on new, patterns that are coming in?
Yeah, the disturbances would change like, okay, this is all sitting on a spacecraft. Imagine on the spacecraft, there's a wheel that's spinning and that wheel is spinning and it starts at, let's say 50 hertz and then it goes to 100 hertz. That wheel that's spinning, maybe that's changing over a time scale of a few seconds. These things are going, you know, potentially kilohertz. So that there's a time scale separation where like they're able to learn much faster than, not completely what you're saying. Yes, there is an issue of like, can you learn fast enough to keep up with the disturbances? But they tend to be changing at a low enough frequency where you can actually change and keep up with them.
So most of the disturbance is coming from onboard systems, is what you're saying?
Yeah, a lot of it's coming like this structure is not, this is not perfectly damped from the satellite. And so the, you know, the structural path from the satellite up to the mirrors, that's where a lot of these disturbances are coming from. Yeah. Okay. Okay, so this was the case without model error. Now imagine I add just a little bit of model error. The loop bandwidth, I think, was 12 radians per second. I'm going to add a little bit of extra model error out at 50 radians per second. So this is, normally when we do classical control, this wouldn't have much effect at all. And sure enough, again, for the first 10 seconds, this is without the recursive least squares. This is almost the same as the plot on the previous slide. That's kind of this first point is like, in classical controls, that would be like, no problem. There's always a little bit of model error. It doesn't affect the linear time invariant control at all. This is why we, you know, relied on linear time invariant control for years, is because like, does good enough. Not so affected by things that we don't know. Great, okay. On the other hand, this thing works great. If I know the model, I added just a little bit of model uncertainty, okay, and it starts going unstable, okay? If I add just a little bit of time delay or a little bit of like high frequency resonances, it's very easy to cause this to go unstable. So that's kind of the crux of the issue. So now you might say, great, okay, we're using online optimization to learn the disturbance. Why not just learn the model, right? We have lots of results, especially in the recent literature. Let's learn the model. A lot of them assume something about the state dimension. I have an upper bound in state dimension. That may seem like a minor assumption. It's not though, because like these type of applications, the model is in principle infinite dimensional. You know, it's a structure. You model it with a PDE. The mirror themselves, even you model with a PDE. We're making finite dimensional approximations. There's maybe small nonlinearities. So even an assumption that you believe there's a finite state dimension and you're going to learn the model, not so easy. The other reason it's not so easy is the following. Most of the disturbance is happening at lower frequencies within the control bandwidth. And I've tried to motivate that there are learnable features here. Yes, there's white noise, but there are learnable features. This would be more representative of dynamics that are electromechanical with some flexibilities. This is from a hard disk drive, but it's a similar effect. Magnitude and phase versus frequency. This is 50 hard disk drives in blue. The red is a model that you might use for design. Okay, the model is reasonably accurate at low frequencies. There's errors, but you know, it's reasonably accurate. You go to high frequencies, they all look slightly different. In principle, it's infinite dimensional because like in a hard disk drive, it's basically a piece of steel that you're moving back and forth at a high frequency. You may think that's rigid, but it's really, you know, at high enough frequencies, it's got some flexible effects. That's kind of what all these are saying. And it also changes depending on the temperature, depending on aging. So it's very hard to learn these things at high frequencies. And so the argument that I'm going to make, or what we're going to try to do in the rest of the talk, is say, let's stick with trying to learn the disturbances. Let's hope we have a good enough model, but let's try to be robust to small errors. And that's what we're going to try to do. That's the last piece. So how are we going to go about doing that? Well, first off, we needed a way of bounding what, how much model error we believe that there is. So let's stick with, just to explain this, let's stick with this example that I just gave. There's 50 of these blue ones, and I've got one design model. How much error is there? Well, one way of measuring the error is to take the red minus one of the blues, divide by the red. That's relative error. Okay, so 5% would mean there's a 5% deviation. Because this isn't a log scale, if you zoomed in here, it may look small, but in an absolute sense, the error is pretty big here. The error is pretty small here, right? Because we're working on a log scale, but in a percentage sense, this is what it looks like. Okay, so these are the relative errors of the 50 blue ones relative to the red. They're very small. Minus 40 dB is 0.01. That's like 1% relative error at low frequency. The model is very accurate at low frequencies, and then at some point it's just very large. You shouldn't trust the model. Okay. So the way we're going to model this, there's lots of ways that people kind of in the robust control literature might model this, is to say I've got a basic model. I'll call that G naught. That's the red one. And I'm going to add a little bit of error here. And I've in this architecture, this is a multiplicative or relative error, and I put a bound on how big that error can be. Okay, so think of this kind of purplish thing as maybe being a bound. I might use a more crude bound for numerical reasons, but that's kind of the basic idea. Okay, so I can tell you how big the error can be. It can be that this could be infinite dimensional as long as it's linear time invariant. Okay, so we're not making any assumptions about the state dimension here. We're just saying this is how far away the actual dynamics can be at each frequency. Okay. Okay, I already said that. That's the relative error bound. Now we're going to come back to this recursive least squares. Where we had the original plant dynamics, we're now going to insert this thing where there can be model error in addition to the design model. The recursive least squares block has a couple things going on in it. It's got an estimator to estimate W hat, and then it's got this time varying piece where we've estimated the disturbance, then we predict the output, and we keep updating these coefficients. So that turns out to be linear time varying. And so the way we're going to do our analysis is we're going to separate all the easy things from all the hard things. So a bunch of things here are time invariant. That's linear time invariant. That's linear time invariant. There's an estimator down here that's linear time invariant. We're going to play some block diagram manipulation, put all the linear time invariant stuff down here. We've got the model uncertainty. We'll just kind of separate that for the moment. And then we've got this FIR filter that was time varying. I'll separate that out as well. Okay, so I'll just separate out the things that are hard to sort of analyze, either uncertainty or time varying pieces from the pieces that are easy to understand. Our question now is, I've got this time varying online optimization. I've got this model uncertainty. If I can tell you a bound on the model uncertainty, can you somehow prove to me that this will be stable? Like I put in a disturbance, at least this will be bounded. And do I have to modify this at all to get that stability proof? Okay. Okay, so that's the key question we want to answer. And so this is kind of the crux of the result in Joyce's paper, is that yes, you can do it. There's a version of the small gain theorem that we're using here, which I think in maybe 562, which is the nonlinear class, they might talk about that. Maybe we briefly talk about this in 565. But the technical result is if you tell me a bound on the uncertainty, we've normalized it just to be 1 just for simplicity in the proof. If you bound this piece as well, so you don't allow it to vary, you just artificially kind of limit it. Think about, I'm going to allow the recursive least squares to work as long as it stays within a certain range. Then there's some induced norm condition you can solve, and there's some free parameters that you get to pick here. Okay. And if that condition holds, then you will be stable. Okay, that's all we say. All right, so that normalization is just to make the result simpler. You can do this in any induced norm you want. If you do this in the norm that's the induced 2 norm, this is an old result, related to structured singular value analysis. We're going to do this in a different norm for reasons that'll be useful for our online optimization. So we're going to do this in the norm where we're doing it in the induced infinity norm. So we're going to measure the L infinity norms of all these signals. There's a whole textbook on this type of analysis, and that'll be more useful for us. Now, why will that be useful for us? I'm going to skip kind of the proof here, but the basic idea is the following. We're going to put a bound on this recursive least squares component in the L infinity norm. It turns out that can be implemented at each point in time just by taking your coefficients and scaling them down to satisfy that. That's why this is a useful norm. So we'll solve the recursive least squares problem. We'll have done some analysis to say that if you just limit the coefficients, you're still going to be stable. Okay. So here's kind of the whole summary of all the details. We determine a bound on the uncertainty. We may need to normalize. There's a normalization that happens. We apply this small gain condition that I had in the previous slide. That we do this calculation, that'll give us a bound that we can put on the FIR filter. If you restrict the FIR filter to stay within that bound, then you're guaranteed to have stability. Online, then you would solve the least squares problem or whatever online optimization you want. You'd add one additional side constraint. You'd limit the gains of the FIR filter. So that gives you a constrained convex optimization. If you do this online, you will definitely be stable. That's kind of the point of all this. This similar method works for other online convex optimization methods. Okay, so I just have a few minutes left. Let me just give you one quick example. I'm going to switch gears now and maybe give you an example. I said there's lots of recent work on doing online convex optimization from people maybe coming from a more machine learning background. This would be kind of one case. The structure is pretty similar. In their paper, they have a disturbance at the plant input. They again have an estimator. They were looking at state feedback, so they have a baseline state feedback law. And then they have a piece that they're learning how to reject the disturbance online. Again, they're using this regret-based formulation. So they're not using recursive least squares. They have some other optimization that they're solving at each point in time to figure out what the filter coefficient should be there. The details are in that paper. They're not super important for what we're going to do. We're just, again, going to try to figure out, will this be stable? And if so, what sort of limits can we put on this path to ensure that we stay stable? Okay. This is a simple academic example now. We've got a first order plant. The disturbance estimator is given there. The thing that they're trying to optimize is an LQR cost. So Q and R are given there. And here's their baseline, here's their controller. They've got a baseline state feedback and they've got this disturbance cancellation part. Okay. So here's what it looks like. I'm going to put a limit. I'll say what the outcome of our analysis was for a minute, but let's suppose I limit the output of their online convex optimization on this axis. So if I set the limit to 0, that means their online optimization isn't doing anything, and I get just the state feedback performance. So this is the average LQR cost on this vertical axis. If you allow their online convex optimization to work with kind of no limit or no bound, that would be going out in this direction, you get this performance. And everywhere in between, we've kind of filled in. There's no model error yet. Okay, so definitely their online optimization makes things better. Lower cost is better, so their online optimization does better than just doing the baseline state feedback. We then add the model uncertainty. So this part I'll skip, but it's kind of the same idea. We add some uncertainty to the plant. We run our analysis. Given the model uncertainty that we've measured, we say, if you make the bound this level, 1.06, you will definitely be stable. So you can run their online optimization and limit the output to this level, you will be stable. We then sample a whole bunch of uncertainties. And for each value of beta, we run their algorithm. And sure enough, a bunch of them eventually go unstable if you go kind of too large. So this says a couple things. By limiting the output, we're not getting the full benefits of the online optimization because we're artificially restricting what the online optimization can do, but we're also saying stable. So there's kind of a trade-off here between how sensitive or robust are you to the model uncertainty, but you're also giving up some of the performance in doing this. Okay. There's another example I should have said. This was using they had a time horizon of 1 step in their FIR filter. You can do the same thing with 5 steps and you get kind of similar results. Okay, so I think I'm out of time. So let me just kind of come back to the beginning. This is the slide I showed at the beginning, which is online optimization can be used to improve performance or disturbance rejection, especially in high precision applications. The point I tried to make is that small model errors can cause you to go unstable. And then the key contribution is just to think about, well, how can we come up with conditions that will allow us to still get some performance benefit, but not be so sensitive to model errors. The L infinity norm was just useful because then in real time, every time step, we can implement this constraint. Okay, with that, I'll stop if people have questions. Yeah.
Excellent talk. Thank you. I guess I have two short questions. Number one, your RLS algorithm. Sometimes people include forgetting factors in order for the RLS algorithm to be able to adapt automatically to change the disturbance. Does anything here change, include forgetting factor?
No, okay, what I'm gonna say is both good and bad. No, nothing in our robustness analysis changes, which is good in the sense that it's simple, but in our analysis, we never took advantage of any part of the time varying structure. We just say if it's time varying, it's gotta be within this range. So it'd be better actually if our algorithm did take advantage of that knowledge, because then we could get kind of wider range on like how we're gonna allow you to operate the algorithm. Bigger, bigger limits is what we would like to get.
So my second short question is, your examples are all examples of, were the examples that you showed us where you were assuming something for the disturbance were sort of a non-ergodic disturbance, like a sinusoid that persists together with white noise. And I'm curious if there's, I mean, I know with, for example, for these RLS algorithms and so forth, it's a little bit more challenging if you're talking about filtered noise. Is there a reason why this kind of approach is better for the disturbance you showed, or does it work just as well in case of filtered noise where you actually have to?
Yeah, I guess what I'd like to separate is what's the online optimization you're running, which depending on what you do, may be better or worse if there's filtered noise or just pure sinusoids. From our result, which is like, no matter what you try to do online, if there's a time varying part, we can tell you like what limits will ensure that you're stable. So in a certain sense, like our result isn't about like which algorithm is better for a certain type of disturbance, although we should look at that. Like our initial result just has to do with like, is it stable or not? Now, getting to your question of like, should we do something different? I'll put it this way. So I did recursive least squares. I did this online optimization. There's a whole nother set of types of things that people do where they say, I believe there's like small number of sinusoids, so I will just try to learn, like do phase lock loops and try to cancel those things out. I think there's a whole host of things, so I don't have like a simple answer to that. Like short question, but long answer, I guess is the, yeah, I don't have a good answer. Yeah, go ahead.
Which, in the elegant results you got, which was the hardest part that you felt happy to solve towards it? And maybe in that related aspect too, and that companion thing, what do you suspect is true that you right now don't know how to solve, but would like to solve next?
This is I'll answer your second question and come here. This is the second time I've given this talk. The first time I gave it was in Stuttgart, and a colleague of mine said, oh, that's fine, but you're kind of, he put it much more nicely than I'm about to say. He said, you're kind of doing a Band-Aid. You solve for the algorithm, and then you put limits on the output. Like you should be integrating the design. You should be designing the algorithm so that it's initially, like have a version of the recursive least squares that's robust to model uncertainty right from the start. And that's the thing that I think would be really nice to solve, is like jointly solve this problem, which is not what we've done. We've said someone gives us the algorithm, then we're just going to artificially limit it so it's stable. Now, your first question was like, what it was nice to solve. I think when I initially did this, I had a preconceived notion of what the result should be. This part's technical, but it's just stuff that I've worked on in the past that I initially had a preconceived notion of what should happen. There's various norms when people do this that people use. The norm, the induced L2 norm, which is what most often appears in these problems, like that's going to be the thing that works. Now, it turns out for various technical reasons, if you're trying to solve online optimizations, the fact that you can use any norm here is useful. This norm that most people use is for doing offline analysis. So there's some other induced norm that turns out to be much more useful for online, something I had not thought about. And so it's just kind of cool to see like, oh, this other norm that I've kind of in this one book, but it's not, most people don't usually see it. It's cool to see it pop up in a different way for well-motivated reasons. So. Any other questions? Yeah, go ahead.
I'm curious, so sometimes small gain type of analysis is conservative.
Yeah.
Do you have a sense of conservative chart?
I have a conjecture that it's sharp if you have a single full uncertainty, which means I believe we could find a sample, plug it in here, and the blue curve would go unstable here. That's a theoretical, it's not that conservative. As a practical matter, probably fairly conservative. Even then, it's still nice that this is a foundational theory. You could think of this beta as like a tuning knob. And you could say, from a practical point of view, I'll start with a small value. As long as it's stable, I'll increase. If it goes unstable, I'll maybe back off a little bit. So it gives some theoretical like foundation for why you might want to do that. So that would be my answer. I would say for practical reasons, agree that this can be conservative. Any other questions?
You know, the chat maybe.
There are not any in the chat, so I'm safe. They haven't gotten used to it this semester. They don't know they can do it yet.
2020 is too old.
Okay,
Yeah.
yeah. Yeah, we'll do one more and then we'll break.
So part of your analysis, I mean, I understand it was just analysis, it's not something necessarily doing the algorithm, but it requires that you take the output divided by t and get and identify but 2t, right?
Yeah.
So now that got me wondering whether or not there's does the relative order of t really matter? Do you have to make assumptions on that in order for this to work? You have the t rolls off very quickly, for example.
The short answer is yes. So first off, if t is rolling off, the inverse of t is rolling up. If you take a snapshot of what the recursive least squares is doing towards the end of the simulation, it's got very high gain at high frequencies, which is also part of the reason it ends up being very sensitive to model errors at high frequencies, because you've just added something very high gain at high frequency, which is not a good property. So yeah, and then not even to worry about things like right half plane zeros, then you've got these inversion effects. So most of these proofs would have like assumptions about, you know, are there right half plane zeros or not for stability? Yeah, I've kind of sidestepped that and into this kind of talk. Yeah, good question. All right, I think that's probably it for time. I'll hang around if people have questions, but thanks for joining on the first one.
Approximation of the
Yeah, it's brutal. Like, you know, you think of the classic adaptive control text and direct adaptive control. What is getting? Well, I'm not through his work. Yeah. So you're in your.
Yeah, actually, now it isn't, yeah.
It's very easy to show.
You want to have a talk now or you want to
I see next one. I just.
Press too soon.
Yeah, basically I did.
Happy late. I also tell us yesterday in our meeting, I'm very late.
I feel like you're ready to go.
Yeah. You run into problems with more or less. You're able to identify exactly the right. Yes, policy is not identify exactly the correct. So. I'm still kind of thinking about your talks. I'm not sure if that even really applies because you're identifying that by our filter, which is. Standard RLS algorithm, which would identify
that one we did. Yeah, it was applying, right?
Yeah, it's essentially just a moving average filter, so it's probably worse, but it just